Uh, Hello, welcome to another lecture on expansion of Navier-Stokes equation in polar coordinates. So, we start with the Navier-Stokes equation in vector form. Navier-Stokes equation in vector form like this: dou u by dou t plus u dou del dou u and taking u is equal to ur er plus u theta e theta and del is equal to er dou by dou r er cap e theta dou by dou theta and we do this expansion and this is called a coordinate free form. Coordinate free form which can be expanded to for any coordinate system. So in this present lecture, I am trying to expand this Navier-Stokes equation by using the Cartesian, using the polar representation, polar coordinate representation, in which u is like this and del vector is vector in terms of the unit vectors er and theta. And the intention of this derivation is to show how there are certain extra terms coming when you are expanding the Navier-Stokes equation in polar coordinate system. If you compare these equations in polar coordinate system and Cartesian coordinate system, we see few extra terms. How these extra terms are coming? Basically, these extra terms arise due to the variation of ER and E theta vectors in the tangential direction. In space, ER and E theta varies, not like IJ. IJ vectors are vectors which are the same if drawn at any location. So spatially, I and J are not varying. Whereas if you look at ER and D theta, we will see that there is variation in the variation when you are drawing these unit vectors at different angular positions. So for example, to show that, I will plot this. I will make this sketch of this unit vectors x, y, and we draw an arc of a circle. This is an arc of a circle of a constant radius. Let me assume that the radius is unity. So the radius is unity. Then these are two radial vectors of unit length drawn at some theta and some other theta. Some other theta. This theta. Let me mark it as delta theta. So this is the ER vector because its length is 1 and along the radial direction. This is a theta and this is ER at the theta plus delta theta. And actually these two vectors are different because there is you can draw a difference d vector. So that mathematically it can be written as so this vector is a vector marking it as a d vector. So mathematically, so vectorically I can write as er theta plus this d vector is equal to er of theta plus delta theta. So that this difference is er of theta plus delta theta minus er of theta. And if you look at the magnitude of d, which is the magnitude of er multiplied by delta theta. For smaller delta thetas, the length of the d vector can be written as delta theta. Delta theta into unit vector along the d direction. So that is er theta plus delta theta minus ER cap at theta, so that this unit vector is ER theta plus delta theta minus ER theta divided by delta theta, and in the limit delta theta tending to 0, we can say that these are tending, then the d vector is along the tangent. This d vector is along the tangent. So that is the tangent vector. Tangent vector is basically E theta vector, and we are talking about unit vector. So this d cap is E theta vector, and that what is this differentiation? This is a differentiation dou ER by dou theta. So similarly, we can also see that this is ER vector. There is a spatial gradient with respect to theta that gives you E theta. In the similar manner, we can derive that dou E theta by dou theta is equal to minus ER, which is radially inward unit vector. So these partial derivatives of ER and E theta with respect to theta are not equal to 0. Whereas if you draw a unit vector at the same angle, same radial unit vector along the same angle, this ER vector and a shifted same angle at a shifted radius, some another ER, these two ERs are same because they are parallel and equal. So there is no gradient in the radial direction. So dou ER by dou R equal to 0. Similarly, dou E theta by dou R also equal to 0. So when you are differentiating with respect to unit vectors with respect to radius, there is no change. Whereas when you are differentiating partially with respect to theta, there are some results. Non-zero results are there. So that makes some extra terms. So let us first try to expand this term and see. U dot del of u dot del. So u dot del is UR ER plus U theta E theta dot del is ER dou by dou R plus E theta dou by dou theta, right? This is this one. And what does it give? What does it give? U R dou by dou R. This one plus there is a divided by R is there. So U theta by R dou by dou theta. The whole into this U is there. This U you can write as U R E R plus U theta E theta. And if you look at the differentiation of with respect to UR dou by dou R, dou by dou R differentiation on ER and D theta are zeros. So you can expand this as UR by dou R, dou R. This ER is outside the differential coefficient because it is a constant, it's not varied. So similarly, this one, if you do for this one, UR dou by dou R will be operating on U theta and E theta is out because this is radial direction. So E theta with respect to radius direction is constant. Whereas if you look at these differential, those differentiations, U theta by R, dou by dou theta, UR ER. So we have to differentiate this as a product. We cannot take ER outside. Plus U theta by R dou by dou theta of U theta E theta. And this term I will just copy down. Just copy this one. This is not cannot be further simplified. So that cannot be further. There is no further simplification of this. Whereas if you are trying to differentiate this, so I am going to have u theta by r. This has to be differentiated as a product. So first ur is taken outside, dou er by dou theta plus next ur is differentiated, dou ur by dou theta into er outside. So similarly here it is u theta by r into dou. So u theta is constant and taken outside, and dou e theta by dou theta plus dou u theta by dou theta into e theta is taken outside. So again, this is equal to this time again I paste. Okay, so again the copy. So this is saying plus this is u theta into u theta into ur by r, dou er by dou theta, is e theta. This result is e theta. And plus u theta by r into dou ur by dou theta er, that is this product, plus u theta into u theta is u theta squared by r, dou e theta by dou theta, that is minus er. So there is an er will come with a negative sign, so this term becomes minus, plus u theta by r into this dou u theta by dou theta e theta. So when we are doing this expansion of this, if we get the vector equation like this, there are some radial terms. This is the radial. This comes in the radial direction. This comes in the radial direction. This comes in the radial direction. So there are three terms in the radial direction. So if you rewrite the terms in the radial direction, it is ur by dou r plus u theta by r dou ur by dou theta minus u theta squared by r. So u theta squared by r, this term, and this term, the whole into er. That is, this radial component is like this. And plus the other term will be ur dou u theta by dou r plus u theta by r dou u theta by dou theta plus ur u theta by r e theta. So these four terms are there in the Cartesian coordinate also. This extra term and this extra term. This term is in the radial direction. So this is all these terms are acceleration terms. So this is the radial direction, inward radial direction. This acceleration term is centripetal acceleration. So this centripetal acceleration is something which we experience when some particle is rotating in the tangential direction with a velocity u theta, that is tangential velocity, that experiences a radially inward acceleration, that is called centripetal acceleration. So basically that physical acceleration is hidden in the mathematical simplification. It comes out. It is because of the differentiation or the variation of the radial and tangential unit vectors in the theta direction. So similarly, if you look at the tangential momentum equation, tangential acceleration, there is one acceleration. This is called Coriolis acceleration. Coriolis. So this is actually when the slider crank is there's in the slider crank mechanism. the crank is rotating, and there is a slider is there. There is a element in that slider that moves in the radial direction along the slider, sliding passage. At the same time, the crank is rotating. So it has got u theta and ur. That is a radial velocity as well as tangential velocity. In that case, the slider crank mechanism will be accelerating in the tangential direction. So that acceleration is called Coriolis acceleration. So these are the two extra terms as far as the acceleration time is concerned. And the next the extra terms arise due to this one. This is actually viscous term. So if you look at the viscous term, so that is mu into del squared u vector, del squared u vector. So the Laplacian operator on this vector. So okay, the time being, I will not, I will exclude that nu, and we'll see what is del squared u vector in polar coordinate system, and the Laplacian operator operating on this vector. So you can see that the Laplacian operator for the polar coordinate system is dou squared by dou r squared plus 1 by r dou by dou r plus dou squared 1 by r squared by dou theta squared. So this is the kind of expansion for del squared operating on ur er plus u theta e theta, and out of which this differentiation and this differentiation are along the radial direction. There are no extra terms. No extra terms arise due to this radial differentiation, whereas extra terms comes because of the tangential derivation along the tangential direction, and that too second derivative. So we will see what are the extra terms comes out of this 1 by dou squared by dou theta squared. So for that I will consider dou squared by dou theta squared. Dou square, the 1 by r will consider later. So dou squared by dou theta squared e on ur er plus u theta e theta. So we'll see what are the extra terms coming. So this is actually first we will do dou by dou theta, and then first I will do the dou by dou theta first. Then again once again we will do dou by dou squared by dou theta squared. So the first stage differentiation of this would come as dou ur by dou theta into er plus ur into dou er by dou theta plus dou u theta by dou theta e theta plus u theta into dou e theta by dou theta. So that is okay. So this is equal to dou ur by dou theta er plus this dou er by dou theta. Dou er by dou theta is e theta. Ur e theta plus dou u theta by dou theta e theta plus u theta into dou u theta by dou theta is minus er. So I'll write it as minus er here. So this is only dou by dou theta. What actually I want is dou squared by dou theta squared of ur er plus u theta e theta, and that will be equal to dou by dou theta of the whole of this. The whole of this will take so this is equal to dou by dou theta of the whole thing. So Once again we have to do it. So I will take this to copy the entire thing. Take this. So this is what it is. So this is equal to this. So this is equal to. So again you have to do. So again you have to do means this will become dou squared ur by dou theta squared er plus dou ur by dou theta into dou er by dou theta plus this one dou ur by dou theta e theta is outside plus ur into dou e theta by dou theta plus when you are doing this one dou squared u theta by dou theta squared e theta plus dou u theta by dou theta into dou e theta by dou theta minus dou u theta by dou theta into er minus u theta into dou er by dou theta. So we will get, we have to simplify it. So this is dou er by dou theta. Dou er by dou theta is e theta. And here dou e theta by er is minus u minus er like that. This is also minus er. This is e theta. So let us write down. So dou squared ur by dou theta squared er plus dou ur by dou theta e theta plus dou ur by dou theta e theta. And this is dou ur by dou theta e theta. This is dou ur by dou theta e theta. That together we can write as twice of that. So these two things become together twice. Okay. So that is this is ur er. This is ur er. This one is dou squared u theta by dou theta squared e theta plus dou u theta by dou theta. Dou e theta by dou theta is minus er. So there is minus er of the same thing. So the entire thing becomes minus twice of that. Minus u theta dou er by dou theta is again dou er by dou theta is u theta. So it becomes u theta squared. And then you also not so u theta squared, but u theta into dou er by dou theta is dou er by dou theta is e theta. So that is it. So actually this is not 1 by r but 1 by r squared. So this term earlier actually del squared 1 by r dou by dou r 1 by r squared dou theta squared. So there is a 1 by r squared is there with this term. So everything the final equation will have a 1 by r squared multiplied. So 1 by r squared. So 1 by r squared will be multiplied with all radial unit vectors. So dou ur by dou theta squared. This is this is plus ur er or minus ur er. I have to check. So this er comes because of dou u theta by dou theta is minus. Actually minus er. This is minus er. So there's a minus er is there. So it is ur by r squared. Ur in r squared will come. So minus twice dou u theta by dou theta, the whole into ER. Again here also plus 1 by r squared. E theta terms will write. E theta terms, the first E theta term is okay, 2 dou u r by dou theta. Then next is plus dou squared u theta by dou theta squared and E theta here minus u theta. Okay, this r squared here it is not there. If 1 by r squared is the 1 by r squared is for all the terms. So here also r squared. So here if you look, we can have this r squared here. 2 by r squared. This is 1 by r squared. This is r squared with theta. So in the okay, this term is similar to what is there for the Cartesian coordinate system. This term is also there similar to Cartesian coordinate system. The extra terms coming here are these terms, these two terms in the radial direction. So in the radial direction, we are having two extra terms. So ur by r squared and minus 2 by r squared dou u theta by dou theta in the radial direction. Radial direction. So these are the extra term, and the tangential direction minus u theta by r squared, u theta by r squared minus plus 2 by r squared dou ur by dou theta in the tangential direction. Tangential direction. So these are the extra terms. So altogether, we can write for polar coordinate system the expanded form of the Navier-Stokes equations are dou ur by dou t at the time derivative, dou ur by dou r plus u theta by r, dou ur by dou theta minus the centrifugal force, it's not centrifugal force, centripetal acceleration along the radially inward direction, and this entire thing is multiplied by ER. So we will write for the radial coordinate, radial direction, momentum. This is a radial direction, we have this minus 1 by rho, dou p by dou r plus mu into that will be the dou squared ur by dou r squared plus 1 by r dou ur by dou r plus 1 by r squared dou squared ur by dou theta squared minus we are having this extra terms, these two extra terms. So that is minus ur by r squared minus 2 by r squared dou u theta by dou theta. So that is, this is for the radial direction, tangential direction. Tangential direction, the Navier-Stokes equation for the moment, okay, the momentum part of the Navier-Stokes equation will be dou u theta by dou t plus u r dou u theta by dou r plus u theta by r dou u theta by dou theta plus the Coriolis acceleration is equal to minus 1 by rho dou p by r dou theta plus mu into dou squared u theta by dou r squared plus 1 by r dou u theta by dou r plus 1 by r squared dou 1 by r squared dou squared u theta by dou theta squared plus there is a term of plus is this one 2 by r squared dou by dou theta of u r, then there is a negative term minus u theta by r squared. So these are the expanded form of the Navier-Stokes equation, where we have this extra term, and this is Coriolis acceleration term, and here there are two terms for the radial momentum equation and the centripetal acceleration.